Hey there, Mr. Brown here, and this video represents the notes for Chapter 3 from Klein's Organic Chemistry text. And Chapter 3 is all about acid-base interactions, acid-base reactions. We're going to learn how to define and even predict some acid-base interactions between different molecules. So if you'll follow along with me, we'll start by defining exactly what an acid-base interaction looks like. So you may remember from Gen Chem the Bronsted-Lowry definition of an acid and base, which is in an acid-base reaction, an H plus ion, or what is, if you think about it, a bare proton, is transferred from one molecule to another. This is the simplest and perhaps most common chemical reaction. It is taking place in many different solutions, kind of ever present at all times. This is just, like I said, perhaps the most simple. Like there are in any aqueous solution, particularly of biological importance, there is very often always some acid-base system between a pair of molecules that is set up in which they are trading back and forth some bare proton, some regular hydrogen atom without the electrons. And so when this is taking place, we have special definitions for it. We call it an acid and base reaction. The acid is defined as the molecule that is giving away the H plus proton, and the molecule that is receiving that proton is considered the base. And so if we're looking at our examples here, we see an HCl, we see the classic reaction. HCl reacts with water to give us the hydronium ion H3O plus the chloride ion Cl minus. And so this is a chlorine with 8 valence electrons. It's received 1 electron from somewhere. And the way this works in kind of the organic view, if you will, we see our HCl molecule in the Lewis structure form here, so we can see all of the electrons and the bond between hydrogen and chlorine, and we can see the Lewis structure for water here, classic bent shape with the 2 lone pairs on the oxygen. After the acid-base reaction has taken place, the hydrogen here has reacted and moved over to the water. It's now bonded to that water molecule. So that's why this is the acid, because it gives the proton to this species here. That makes, in this case, the water molecule our base, because it now has a new proton associated with it. However, notice no electrons move. That's going to be an important point that we investigate and cross all of this discussion of acids and bases. The 2 electrons here in this bond between hydrogen and chlorine stay with the chlorine. That's why we end up with a chloride ion over here instead of just a neutral chlorine atom. That's why it has a negative formal charge, because it keeps both electrons in that bond. Only the positively charged proton moves from here to here. And so we see in the new, and it uses one of those lone pairs to form that bond. So in the new structure, we now have an oxygen that only has 3 bonds in 1 lone pair, and so it has the positive formal charge to balance out the fact that we're neutral over here. We need to be neutral on this side, and we do that by having a negative charge here and a positive charge here. So those are the simple definitions of what the acid and base are in acid-base reactions. On the next slide, we'll go even deeper and talk about the conjugate acid and the conjugate base. And as I just mentioned, now we're going to take a second and define the terms conjugate acid and conjugate base. And all these things are is what the acid and the base from the reactants are turned into and what they're referred to as in the products. We have an example down here, and in this case, we flip things around a little bit. Notice that we have, get the laser pointer out. Notice that we have the base, a base species here, and an acid species here. And what may be different here is, notice this is a water molecule, but in this acid-base interaction, our water serves as the acid, which means it is going to give up one of the H's that water has. And we see that take place from reactants to products here. We see this hydrogen here, they labeled it in red, leaves the water species and bonds here at this negatively formally charged oxygen that has 3 lone pairs, and we form a new alcohol species. So what was the base now has that proton and could give that proton up to something else. So it becomes an acid through that process. When it receives the proton, it becomes, on the other side, what we now call the conjugate acid. So the base becomes the conjugate acid because it now has a fresh proton that it may want to do something with. It may not. It may really like that proton and just hang on to it, but it may do something with this proton, so it becomes the conjugate acid. And the acid, in this case water, becomes the conjugate base. When it gives up that proton, it's now got 3 lone pairs. Remember we said on that earlier slide, it keeps the 2 electrons in this bond here. It only gives up the H plus proton. And so now he's got 3 lone pairs and a negative formal charge. That's a good spot to actually go out and bond something to. It's a good spot to go out and get maybe a hydrogen from somewhere. So now this is a decent base. And so we consider the acid to become the conjugate base through the acid and base interaction. It's really important to get these terms understood and not mixed up throughout the rest of the chapter. We'll talk a lot about conjugate acid and conjugate base pairs as we move through this discussion. So go ahead and get a handle on that. So here we're going to take the opportunity when we're talking about acid-base reactions to talk about how curved arrow notation is used in chemical reactions to show the mechanisms of reactions, and specifically it shows the actions of electrons in our chemical reaction pathways. These are very much like the arrows, the curved arrows that we used in drawing resonance structures. However, there are a few different rules for curved arrow notation when we're doing chemical reactions. So similar to curved arrow notation for resonance structures, curved arrows in reactions should always start on electrons, whether that be a lone pair or a bond of some sort. Arrows show the movement of electrons, and so they should always start on electrons, never on an atom. However, unlike resonance structures, arrows used in reaction mechanisms can break single bonds. This is, of course, sometimes that is the whole idea behind a chemical reaction, is the breaking of bonds and the formation of new bonds. And specifically, the proton transfer is always going to require 2 arrows. And the 2 arrows that are going to be used for every proton transfer is going to be the formation of a new bond to the H plus from an existing lone pair, and then the breaking of a bond to H. So we're going to always break a single bond, in fact, in a proton transfer to leave the lone pair on that atom. And we have, of course, a good example over here. We have a hydroxide ion, an OH minus, that includes an oxygen with 3 lone pairs. Negative formal charge is a good candidate for bonding to a proton, bonding to an H plus. He finds a species that is decently acidic, and in this case this is a more organic acid. This is a carboxylic acid structure, but an acid nonetheless, because it can give up this proton here rather easily. And so these electrons form a bond, showing the arrows starting at the electrons and moving to that atom, forming a new bond with that hydrogen. So this is kind of indicative of that bond being formed. The 2 electrons in this bond will be moved over to that oxygen, and we see the result of that reaction is the hydrogen removed from that oxygen, which now has 3 lone pairs and a negative charge, and the previously neutral hydroxide has become our conjugate acid as a water molecule, because now that oxygen is balanced out with 2 bonds and 2 lone pairs. So this is curved arrow notation. This is the first taste of it. We're going to practice doing curved arrows for acid-base interactions on the next slide. As promised, here on this slide we have some examples of drawing the correct curved arrows for some acid and base interactions, and we're going to take a look at these. The first thing you have to do is figure out what happened in one of these reactions. So if we're looking at the first example here, what we may notice is the hydrogen or proton, if you will, at this point here, disappears and reappears maybe at this structure here after all is said and done. So it looks like, to me, it might be easy if we go ahead and draw our lone pairs on the hydroxide ion there and show one of those lone pairs forming a new bond with the hydrogen atom. And then we notice over here that this oxygen has a negative formal charge now, which means there's 3 lone pairs. Whereas before there was only 2 lone pairs because there is no formal charge on there. So that means the electrons in this bond had to be left with that oxygen. And so we draw another little arrow from the bond over to the oxygen showing that that lone pair was left there. We then can say that this was the acid because it gave away the hydrogen atom. This, or proton really, not the whole atom, just the hydrogen ion proton. This is the base, which makes this the conjugate base, and subsequently this the conjugate acid. In the next example, we can see we have this H3O plus here and an H2O on the other side. So this is probably my acid giving away one of those hydrogen ions to this species here, which becomes positively charged after this transformation. So I'm assuming that that is the mechanism that this acid base or this proton transfer takes. So let's try to draw that out with some arrows. If I add, zoomed in a little bit too much there, if I add my lone pairs, make life a little bit easier. This oxygen has a formal charge, so there is 1 lone pair on there. And it looks like one of these lone pairs forms a bond with the hydrogen. And since this oxygen is left neutral, that means there are 2 lone pairs on that oxygen, so it means it had to get one of these. So I would draw an arrow from the bond down to the oxygen there, and that should be the correct curve arrow notation for that particular proton transfer. Moving on a little bit more quickly through the next one, they actually don't show you the hydrogens here that are implicated in this proton transfer, so I'll go ahead and draw them in. A nitrogen with 2 bonds and a negative formal charge has 2 lone pairs, so I'll put 2 lone pairs around this nitrogen. I'll show one of those lone pairs bonding with that hydrogen ion. I'll show one of the, or both of those electrons actually in that bond left with the carbon atom that gets the negative formal charge, and that would be the correct curve arrow notation for that acid-base interaction. In the final one, we can see we use hydroxide as our base again, and a proton disappears from this oxygen here, which becomes negatively charged. So it looks like one of these lone pairs forms a bond with that hydrogen, and those 2 electrons in the bond are left with the oxygen. So those are some correct curved arrow notation for some different proton transfer acid-base interactions. One of the things we're going to learn about acid-base reactions, more so than not, acid-base reactions are equilibrium processes, meaning they can go both in the forward and the reverse direction. And we try to always keep in mind that equilibrium processes are dynamic. So what that means is for a couple of acids and bases in solution at equilibrium, they are sitting there, they reach some point, you mix everything together, and the system reaches some point where you have everything trading this proton back and forth to the sites that we've identified as acid and base, or where the acid and base reaction is taking place. It's taking place continuously, but we reach a point where the concentration of the reactants and the products is stable, even though that this is going on continuously. And depending on what your reactants and products are, you might have a lot of reactant and only a little bit of product, or a lot of product and only a little bit of reactant at any one instant. You may have a system that sets up pretty evenly where you've got equal concentrations of product and reactant all at the same time. A way that we can kind of measure which side of the chemical equation this can be weighted towards is something known as pKa. pKa is basically a rating system for these interactions that's been put together by empirical testing over a number of 100 to 150, if not 200 years of different hydrogens in different chemical situations, like you see on the chart here beside me. So I can't get it right. There we go. Right. So we kind of have an idea for different hydrogens in different chemical situations read their environment within a molecule about how easy it is to remove that hydrogen. And again, we've just arrived at this over empirical determination testing over many, many years, and we've built tables like this that show the pKa of different hydrogens in different molecular situations. Having a higher pKa means the molecule is less acidic and less likely to give up its proton. Equilibrium values, this is really important, and we'll see how this applies later in our work, but equilibrium of a reaction, the side of whether the reactants are favored or the products are favored at equilibrium, can be determined for acid and base interactions by looking at the side that has the acid with the higher pKa value. So in an acid-base interaction, the product or reactant side that contains the acid with the higher pKa value will always be the favored side. That side will be favored and more concentrated at equilibrium. One way I like to think about it, you don't have to think about it this way, but the pKa is a rating of how excited a proton is to be in that particular state. If you look at our strongest acid, our kind of strongest common acid, there's some more exotic species out there, but our strongest common acid is sulfuric acid. What that means is sulfuric acid loves to give this proton here to other things. He loves to give it away. In fact, if that proton had to rate himself how happy he is connected to the rest of that molecule, he rates it at a -9. That's how happy, or unhappy he is to be attached or bonded to that sulfate ion. So that's how I like to think of pKa as a rating of just how excited that proton is to be at that position. Negative numbers are bad. Positive numbers are good. If it's positive, the hydrogen really, really wants to be there. For instance, here in our alkanes, our hydrogens have pKa's of like 50. They love to be bonded to carbon. This is a really, really stable configuration. On the opposite side, we have the bases that are formed when you pop that proton off. And notice there is a reversal of the strength here. Our weakest acids make really strong bases, and there's a reason for that. Hydrogen is really, really stable bonded to carbon. Carbanions without that bonded hydrogen are really, really unstable. They will do kind of whatever they can to get that hydrogen back. Whereas in the reverse case, back to our sulfuric acid example here, The sulfate, the H2 or HSO4 minus ion is very, very stable. We'll talk about how the stability comes from the resonance involved in this lone pair here. Notice it can be spread across the whole molecule here. That keeps it really stable. That is a very happy to exist anion, and it doesn't really go out in search of closing that lone pair up for anything, so it's a very weak base. So that's kind of how we read pKa charts, and we'll see how we can use that to predict the position of equilibrium for some acid-base interactions on the upcoming slides. So we have our first couple of examples here that says determine the more acidic proton in each pair. And these questions are really simply just trying to get you to evaluate the pKa table. In fact, I think every species here is actually represented directly on this pKa table. So let's try to line the pKa's up with the species that we see. If we look at this structure here, this may have already been stated, but this molecule is called phenol, and you can find the phenol structure in the pKa table right here. And it says that red H plus has a pKa of 9.9. Go back. Didn't mean to turn the pen on. So we have a pKa of 9.9 here. And here we have the humble water molecule, and we can see that water sits on our pKa table. One of its hydrogens has a pKa of 15.7. So the question, determine the more acidic proton, this is asking which is easier to give up. Is it easier to give up this proton or this proton? And that's kind of like asking which is less happy in this situation. And we said that pKa is a ranking of how happy a hydrogen is in his situation. This hydrogen is less happy in his situation, so he is more apt to take off and leave, and that makes this one the more acidic proton. Following down the line, if we see this next structure here, tert-butanol compared to water, we can see the tert-butanol pKa is 18 from the table. We remember water from earlier as 15.7. So now we have a different consideration. This hydrogen here now has the lower pKa, the lower rating of his happiness, and so that is an easier to get rid of, more acidic proton in this case here. Our next example compares ammonia with acetylene. Those are those two molecules, and if we go over here to our pKa chart, we can see ammonia has a pKa, or the hydrogen in ammonia rather has a pKa of 38, and the hydrogen in acetylene has a pKa of 25. It looks to me like ammonia has the more happy protons, where acetylene has protons that are a little less happy. So these are going to be the more acidic ones, the ones that are more easy to remove. Did I write that down on? No. Okay, I thought I wrote 18 for a minute. All right, in the next example, we have some pretty standard. We have the hydronium ion, which has a pKa of negative 1.74. And we have hydrochloric acid, and the proton in HCl has a pKa, as you would imagine, very pretty low. That's why it's known as an acid. This hydrogen is highly unhappy here, bonded to the chlorine, so he can be considered to be more acidic. In the next example, the alkane hydrogens have a pKa of 50, where the alkyne hydrogens have a pKa of 25. So this one is less happy with his situation, meaning that is the more acidic hydrogen. And then finally, we see a couple of structures. We see that the hydrogen involved with a positively formally charged oxygen has a pKa of about negative 7.3, which is pretty low. However, we have our very strong sulfuric acid over here. This hydrogen, again, has a pKa of negative 9. He is not happy at all. He is ready to move out at any time. So that is the more acidic proton. That's how you use a pKa table to rank the relative acidity of different protons in different chemical environments. So following that through, I want to show you here how you can use a pKa table to predict the pKa's of protons that aren't necessarily in that exact molecule, but in very similar environments. And so if you see on my table here, I've got some protons that we could kind of outline if we thought about what the pKa's, there I go, going backwards again. Gotta turn on that pen. What the pKa's of these two protons here, this proton here, and this proton here are with a pKa table, even though those protons aren't directly represented in our pKa table, we would probably be able to understand that these two protons are very similar to, I've got to find them on here, that these two protons are very similar to these two protons here. So obviously the ends of our molecule are different, but we can say that these two protons are very equivalent to those two protons. So, and we might not be able to say, hey, these are exactly pKa of 9, but I don't have any problem with that being a starting point and say these are approximately or may have a pKa close to 9, right? And the same goes for these other structures here. Again, this is not a phenol molecule, but if we consider this hydrogen here to have the same very close chemical environment as the ones in a regular phenol molecule, we could say that this one has an approximate pKa of about 9.9. And then finally, this hydrogen here, this is not a simple carboxylic acid like we see right here, but rather a more complex one with a bunch of stuff here on the outside. If I just put an R there, it basically represents this molecule. And so I could say that I don't know that it's exactly 4.75, but I would be willing to bet that that hydrogen has a pKa close to 4.75. So again, you can use the pKa chart to make approximations for hydrogens in similar chemical environments to what is depicted on the table. It doesn't have to be exactly the same. And here on this slide, we have the same question kind of asked a different way. We're trying to figure out what the stronger base is in each pair. And we want to keep in mind that for bases, it works in this odd reverse scenario. Strong acids make weak bases, and weak bases make strong acids. And the reasoning for that is if we look up here on our chart, strong acids have hydrogens that don't really care to be in that environment. So when they make this anion, those things, the hydrogen doesn't want to be back in that position. And so again, the strongest acids make the weakest bases, where the weakest acids make the strongest bases. If we take away one of these protons down here from the alkane structure, that leads to a carbanion, a carbon with not or carbon with a negative formal charge. And carbons aren't electronegative; they're not equipped to deal with that negative charge. It wants to bond something to get that really balanced out really quickly. Carbons like to have 4 bonds. And so if we're predicting which is the strongest base in each pair, we just have to look at the position of the pKa's of their conjugate acids. And so for instance, we see the acetanilide ion, the conjugate base of acetylene, is called acetanilide, is not quite as strong as the conjugate base of the ammonia molecule. So in this case, if we're looking for the strongest base, in a sense, we're looking for the higher pKa to tell us which is the stronger one. So in this case, the ammonia ion, and there I go again, the ammonia ion is the stronger of the two bases. In the next case, we see our two bases here can be found here on our pKa chart, and it looks like the branched version is further down the spectrum there to the strongest base side. In our next example, we want to know if this species or this species, which can be found here and here, is a stronger base, and it looks like in this case water is farther down the stronger base side of the spectrum. In our next example, we have two formerly negatively charged oxygen species, one here at 16 and the other one right above it at 15.7. This one is a slightly stronger base than the other example. So in the next case, we know that this is pretty much the strongest base we have. Carbon does really not like to be sp3 hybridized with the negatively charged lone pair by itself. In the last example, chlorides are more happy being by themselves than hydroxides. So hydroxide is further down that base spectrum. It is the stronger of the bases out of those pairs. So now we have our examples for determining the position of different acid and base interactions, and we're going to try to see if we can predict whether equilibrium favors the products or the reactants for the following acid and base reactions. To be able to do that, what we want to be able to do, one of the things that we have to be able to do is predict what our acid, base, conjugate acid, and conjugate base are. So we're going to start there and see if we can figure that out. In example A here, we see this species gives up a proton, this species collects a proton, and if we were to go the other way, this species gives up a proton here, which collects a proton. So this is our acid, this is our base, this is our conjugate base, and this is our conjugate acid. What we're going to do is compare the pKa's of the conjugate acid and the conjugate base, and keep in mind that equilibrium always favors the higher pKa. So the conjugate, or the pKa of this acid, is 16.0, so I'll put that here, 16, and the pKa of water is 15.7. Since pKa is always going to favor the higher, or equilibrium is going to always favor the higher pKa rather, we could say that the equilibrium would favor the reactants in this reaction. Now they're pretty close, so this would probably be a pretty equal mix, but the overall the equilibrium would definitely favor the products, or sorry, the reactants here, and it would be kind of maybe hard to make the products. You would maybe have to do some things that would force the equilibrium. Remember Le Chatelier's principle. There are ways that we can force that equilibrium to move to the right side. We won't get into that now. Right now we're just trying to figure out, can we determine the position of equilibrium without really changing anything else. In the next case, you'll want to do the same thing. Determine the pKa's of the acid and the conjugate acid and compare them. So in this case, the acid is this species here, and the conjugate acid is our water molecule. In the phenol, we have a pKa of 9.9, and in water, we have a pKa of 15.7. So in this case, our products would definitely be favored. Maybe a good bit more. They're still not very far apart, but our products would be favored. Equilibrium would favor the right side of the chemical equation there. In the next example, trying to get out of the way some, we have HCl. Oh, and I move. There we go. We have HCl, which gives up its proton. Can't get my writer on. There we go, brought it back. So we have HCl, it's giving up its proton. So the HCl is our acid in this case, and he gives it up to a water molecule. So on the other side, the result is the conjugate acid. We're going to compare those pKa's. This one's really pretty straightforward. HCl has a pKa of -7. The H3O plus has a pKa of, I gotta find it myself, H3O plus has a pKa of -1.74. And so equilibrium is definitely also going to favor the product side in this case. Just don't mind my terrible arrows there. In the last example, we have the acetylene molecule here giving up the proton here to the NH2 minus ion to become an acetanilide ion and an ammonia molecule. So this is our acid and this is our conjugate acid. So acid here, acetanilide, or acetylene rather, has a pKa of about 25. And on this side we have ammonia as our conjugate acid. Ammonia has a pKa of about 38. So in this case, again, the equilibrium would favor the products because equilibrium always favors the higher pKa. So now you're equipped to predict, using a pKa table, the position of equilibrium of different acid and base interactions in addition to the ones that we've shown here.